And welcome back, everybody, to our third session on fundamentals of rotating machinery. In this session, we talk about gears, motors, pumps, and bearings. Well, gears anyway, in the 30 minutes we have. We're going to go ahead for gear topics. We're going to talk about gear mesh frequencies and orders, transmission error, sidebands, hunting tooth frequencies, and gear whine and rattle. You want to go ahead and take it away, Scott?
Sure. Yeah, we'll switch to my screen. Okay. So I've got this 48 tooth gear here, and it's on a shaft that spins at 600 RPM. And the first question I'll ask is, what is the shaft frequency? Well, independent of this gear, that shaft is spinning at 600 RPM, and if we divide that by 60, we get the 10 hertz shaft frequency corresponding to the 10 rotations of that shaft per second. So it's a 10 hertz frequency for the shaft. So we can graph that main shaft frequency with a given amplitude at 10 hertz. Now the frequency of the gear mesh corresponds to those 48 teeth. So we have 48 teeth that are interacting per one rotation. So we go back to that 10 hertz shaft frequency and we multiply that by the 48 teeth. So the gear mesh frequency here is 480 hertz. And we can also plot that with the given amplitude. Now the gear mesh order corresponds to the reference shaft, which is spinning at 600 RPM. And that gear mesh order would be 48th order. There's 48 tooth interactions per one rotation of the tracking shaft. Okay. So let's step up our game a little bit here. So now we have a 50 tooth gear, and that spins at 100 RPM. What is the RPM of that 25 tooth gear? So if we live in a perfect world, something that we could simulate, let's say, Chris, I could say that the RPM of the 25 tooth gear with that ratio, that 2-to-1 ratio we have here, would be 200 RPM. But do you think that's really the case?
That would be a kinematic simulation there, Scott.
Oh, okay.
I don't want to give anything away, but we could do a little bit more with that on the simulation side. But
fair
back
enough.
On track.
Yeah, so we would assume that it'd be 200 RPM, but in the real world, there's going to be something that we call transmission error. And so transmission error means that it's not really spinning at that 200 RPM. Okay? So if we want to actually measure the transmission error in a test, what we do is we take the actual RPM measurement of the paired gears. So we take gear 2, and then that theoretical RPM that we just calculated with the math that we went through. And then we can figure out the difference between those two and figure out what that transmission error is. Now that transmission error, if it's 0, means there's no loss and we have perfect transmission. That's almost never the case. And the question here would be, can transmission error change with speed or load? And the answer to both of those questions is yes. So as I go up in speed, I have different shaft frequencies that are being excited, and I might hit different modes of a given shaft, and that'll influence the tooth interaction between two gears. As I load or unload the gears, that's going to change that tooth interaction. And as that tooth interaction changes, then I can either increase or decrease the transmission error that we're having between the gear pair. Okay? So just kind of breaking this down of the process of how we want to look at this transmission error, we can measure the RPM of the driving and the driven gear versus time. Then we calculate the theoretical RPM of the driven gear based on the math and the ratio between those two gears. We subtract that difference, and that gives us that transmission error that we're talking about. We can then look at those time files and perform an FFT and find out what frequency things are occurring at for those RPM differences, and we can look at that angle or position over time. Now, we talked about gear load and speed causing transmission error. There's some additional things that can cause that as well. So if we look at this gear pair and we just have two perfect circles, and we're assuming there's a number of teeth on each of these two circles and that they're perfectly meshed, is what we're trying to convey here. Yeah, go ahead, Chris.
That's kind of what you would get with simulation. Our gear pairs would be perfectly round. I'll go ahead and take it over from here, Scott.
Yeah, perfect.
So, as Scott said, in this particular case, we've got the ideal case, no manufacturing defects. But let's see what happens when we start to, in the real world, Scott's world, have differences. The first is a manufacturing defect that can cause the gear to be oblong or eccentric. So I don't know if the projector shows it, but these were perfectly circular gears. Here we've ovalized one of the gears, so it's no longer a perfect circle. Well, what kind of error is that going to cause in the transmission error? So if we look at gear 1 and gear 2 in the not perfect circle, we can see that every time or twice as it goes around, the teeth are going to get closer together and then farther apart, because this is in two places on this oblong gear, the teeth are closer to gear 1, and on two places they're farther from gear 1. So we're going to see that happen twice per revolution.
Almost like a different loading of the gears per revolution.
Exactly. And so when we look at some test data, which Scott can explain very well.
Sure. So we have the perfect 100th order gear mesh here, let's say, and you can see it's a equal interaction between the teeth per rotation. And just like Chris explained, if I've got this oblong gear, I've got a different loading that's happening twice per revolution. It's a second order amplitude modulation is what we're going to refer to it as, due to that oblong or eccentric gear. And so if I were to look at this and I perform an FFT on the perfect gear mesh, I'd have a solid line at that 100th order with a given amplitude, kind of unwavering. If I perform the FFT on the bottom time signal, then I can see here that I get these orders that are kind of coming off from that main 100th order amplitude. So I've got some harmonics that you can see there on either side. And what we're showing here is that they're actually plus or minus second order. So we've got kind of this second order phenomenon that we talked about that's happening on either side of that 100th order. So we're seeing content at 98th order, 102nd order, and then it decays off of that in that same kind of harmonic. Now, sometimes this is actually a preferred thing. So there's a company that attended one of our seminars in the past. This company was Lightens, and they actually explained that these oblong gears are sometimes desired or wanted by a given customer. And so they make gears that are oblong on purpose. And some of the reasons for that, if we go back to this slide quickly, you can see, if I add in a laser pointer, you can see here that this 100th order that's perfectly meshed has an amplitude of 1, but with this oblong gear, that main order actually reduces, and here the amplitude is lower than what it is here. So there's actually some benefits to this. If you look here, the direct benefits include reduced timing error, reduced and controlled dynamic belt tension, improved drive energy, and noise level. So there's actually some improvements that come with this oblong gear. And believe it or not, I recently learned that when you get a bicycle, they're actually selling the main crank now as an oblong crank. So that's actually an upgrade that you can get with a bicycle, and they tout the same benefits to that, where you get this increased chain tension or belt tension when you are pedaling with an oblong gear. And there's actually some benefits to this. So it's not always a bad thing to have this oblong gear, but it will manifest itself in the data as a plus or minus second order based on that force interaction that Chris explained per rotation.
All right. So the next type of manufacturing defect we can be looking at is an off-center rotation. So the where they drill the hole on the gear is going to have a certain tolerance. It may not, they try as hard as they can to get it perfectly centered, but it's the real world. Things have tolerance to them. So if we look at the case where we shift the center rotation of gear 2, say bring it closer or farther away, that's what's going to happen each rotation as we go around. The gear teeth will be moved closer and then moved farther away with off-center rotation. Oh, test data again. Scott, can you explain this?
So here we have what we call a modulation. So it's a once per revolution phenomenon. So we have that same perfect mesh at 100th order, but now because it's a 1 per revolution phenomenon, now we have kind of these plus or minus 1 or plus or minus first order decaying order content that becomes evident in the data. So the big takeaway here is that when we have oblong gears or manufacturing defects or misalignment, then we start to get these side bands in our data. So where we expect the gear mesh frequency to be, which we're representing here by this blue line. If I add in another pointer. So this blue line here is the perfect gear mesh frequency, and then we'll get these side bands. And based on where those side bands are, plus or minus first order, then we have an off-center shaft rotation, plus or minus second order, then we have eccentric gears or oblong gears that could correspond to a manufacturing issue. That's where these side bands start to appear. Now, you could have a combination of both. And in this case, we're kind of showing that. So this main red line here that I'm tracing with the laser pointer would be the perfect gear mesh. And you can see there's side bands that are plus or minus 1 order and plus or minus 2 order off of that main mesh frequency. So you could see side bands that are first and second order off of that main mesh frequency that correspond to issues in both cases. Here, looking at this color map, you can see that the plus or minus second order is more prevalent. So maybe the issue to look into if you're trying to improve this transmission error or the performance of these gears would be to look at the oblong gear to see if there's something that could be done on the manufacturing side. I think this one's you, Chris.
Exactly. Thank
Yeah.
you, Scott. So we're going to talk about, so one of the interesting things about gear load transfer is when the gear teeth mesh, they will contact on the tip of the tooth, and as it starts to go through the meshing cycle and unmesh, we see how the contact point shifts along the surface of the tooth. And one of the interesting things that's going on is the tooth, on the left, when it first contacts, it's going to be relatively stiff because engineers, we like cantilever beams. You load the beam close to the base, it's really stiff. As you transition out toward the tip, you're getting further away from, you're getting less stiff as you transition out to the tip. So the gear tooth stiffness is going to vary during the rotation. It's a very interesting phenomenon that happens with gears. So what is a prime number?
So a prime number is anything divisible by itself and 1, actually.
Exactly. It's an integer greater than 1, which is only divisible by itself and 1. All right, so these are all highlighted in yellow prime numbers. 2 divides everything else. I keep forgetting that it itself is a prime number. But we can't have gears made with only 2 teeth.
Right.
So what do prime numbers have to do with gears? I'm getting to the point. So in a meshed gear pair, oftentimes one or both of the gear will have a prime number of teeth. And there's a deliberate reason for that. If the more common factors the gears share in their number of teeth, That means certain teeth will engage and disengage more frequently, which means you're going to build in an area where you're going to get more wear and more damage, and you're basically building in where your first failure is going to be. But if they're both relatively prime and you can avoid common factors, then each tooth will have to touch every other tooth before it gets back around to touch to hit the original tooth. So that way you spread your wear out evenly between your gear teeth. What are some other imperfections in gears? Well, we can have profile errors, so problems with the shape of the tooth. Foreign debris, not a good thing for a gear mesh pair. Damage from foreign debris, surface wear, and pitting. Now, what frequency at which a damaged tooth will impact? So in this particular case, we've got a 50 tooth gear at 100 RPM. We've got a 25 tooth gear at 200 RPM. The gear mesh frequency is 83.3 hertz, which means we need to calculate the hunting tooth frequency. So first we determine the common factors. So in this particular case, we've got for the 25 tooth gear, you got 1 and 25, 5 times 5. For the 50, you've got 1 times 50, 2 times 25, and 5 times 10. So that means the common factors are going to be 1, 5, and 25. So we look for the hunting tooth frequency, FHT, is going to be the gear mesh frequency times the common factor divided by the N1, number of teeth on gear 1, times the number of teeth on gear 2. So going back to some algebra here, substitute in to our equations, and we find our first hunting tooth frequency is 1.667 hertz. Second one is going to be at 0.333 hertz, and the third one is going to be at 0.067 hertz. So if we're doing condition monitoring, checking out a transmission system, if we see spikes in our FFT on these frequencies, then we know that, hey, we've got a damaged tooth in the system. We may need to look at an early overhaul, etc.
Yep. And it could be any of those frequencies, right, Chris?
Exactly, any of those frequencies. Next is a couple of things we want to talk about, our gear rattle and backlash. This is due to the fact that to operate properly, your gear teeth there has to be some free play in your gear. If they were designed perfectly to touch and there was no free play, then you wear out your gear pretty quick. So Scott, what are some of the issues that noise types we can get due to this backlash?
Yeah, well, let's talk about that, Chris. Okay. So we have gear rattle and gear whine, and these are two different phenomena that can happen. So gear rattle is, as defined here, it's the noise induced when the teeth impact each other. So they're not loaded at a high force, let's say. And by looking at the color map, what you can see is that we've got the main gear mesh frequency, where that's highlighted here by this darker red line, but you can see that there's some broadband noise shown in this color map that is also around that main interaction. It's also kind of spread out because of those teeth kind of clanging together or interacting and banging together as they spin, kind of what was shown in the simulation on the previous slide. Whereas whine is more of a tonal noise. You can see that tone increases in frequency. So what that's like is a good example I always point to is if you've ever heard a Formula One car as it drives by, it's kind of got that high loaded gears. Those F1 racing cars have a lot of force, acting on those gears. Those teeth are really pressing on each other, and so they're almost whining based on the amount of force going through. So that it's a high-loaded noise that's very tonal with those teeth interacting. Whereas the rattle sounds more like a jackhammer around that tooth interaction. So these are the two main things that happen based on a noise interaction with the loading or unloading of the gears. So if you've got a rattle, the gears are they've got too much play, whereas a gear whine, the teeth are loaded so tightly based on their construction that they give off this tonal noise around the gear mesh frequency. And then we have some gear analysis
simulation
tools.
stuff.
Yeah, some simulation stuff that I'll hand over here to Chris.
Exactly. Thank you, Scott. So we can look at different ways now of simulating gears, going back to that, taking advantage of the fact that there's AGMA or ISO standards that gears are manufactured to. We know that there's going to be contact from the root to the tip. We can start looking at some simulation approaches. On the low side, we could have a gear joint where that's the perfect gear mesh pair. There's never any transmission error. You don't get a lot of information, but it's good for kinematic studies. On the high end, we can make very detailed nonlinear FE models, linear nonlinear FE models, model the gear contact. And while these models are going to take a little bit longer to run, we can get some great information about root stresses and durability, the durability of the actual teeth, because we've got the stress distributions and the contact pressure and all that interesting stuff. In the middle zone is where we like to live for multi-body dynamics, where we can look at things from a system perspective. We're looking, because again, we take advantage of the known profiles, the known contact, the known phenomenon that at the start you're going to get stiffer. Your tooth is going to be stiffer when it's contacting at the root than at the tip. We can develop equations that allow us to calculate those gear mesh forces. With an analytical and semi-empirical approach, we can look at things like rattle, clunk, a little bit of gear whine. When we talk about an advanced FE method, we can definitely do the same things that the semi-empirical approach can, but we can really investigate gear whine, especially when folks start to lighten their gears by putting holes or slots. And we'll explain what challenges that brings. So looking at from a simulation perspective, there are a number of different algorithms we can use for calculating that gear force. At the lower end for rattle, we've got ISO, where you specify a transmission error curve that you could get from my colleague Scott from his test data. You can have a user-defined stiffness, plus again a transmission error curve. Where we start to get really interested is this ISO-Chi analytical approach. Some smart folks developed a system of equations that can account for the varying tooth stiffness during contact and accurately predict the transmission error. If we start to look at things like lightening the gears or more accurate calculations of the tooth stiffness, when we take into account other phenomenon, which I'll talk about in another slide, we want to use our advanced method, which actually uses an FE method to calculate the stiffness of the gear tooth, and we use that in the simulation very efficiently. Now, what are some other things we have to take into account? If your shafts never deform and your gears never wobble or never bend and just stay perfectly planar, which only happens in the simulation world, never happens in the real world, we want to take into account slicing. So we're in our empirical model, you specify how many slices of the gear tooth, and then we can we'll calculate the force distribution through the tooth, and we can take into account how one side of the gear tooth is going to get loaded higher than the other when we start to have misalignments. And then profile modifications. One of the things that can help you reduce whine is to modify, you take your idealized 7 ISO parameters, or I think it's the same for AGMA, yeah, same number of parameters to describe that profile, and then you can add shaping changes at the root or the tip, or at the both sides, and that will, depending on how you shape that and how your gear's loaded, you can reduce the whine. So let's talk about some advanced FE methods that allow us to take into account the varying stiffness of the blank. Basically, we get the main idea from research done by Vedmar, where near contact, the deformation gradients are strong. We know the point of contact, and we can use an analytical solution. But away from the contact, the gradients are very gentle, and we would want to use FE models to understand the stress gradients as we transition, as we get away from the tooth, we go down the blank of the gear to get to the shaft. We would want to use FE methods to understand that stiffness. So our advanced FE method basically superimposes both. Near the contact, we're using our analytical solutions, and as we get away from the contact, we use the FE method for the stiffness. And why do we want to do that? Because as you see in a lightened gear, the tooth stiffness is going, a tooth over a spoke is going to be stiffer than a tooth over a slot. Also, each tooth has its own variation that we've already talked about. It changes stiffness from the root to the tip, and we see those in our primary bands here, the gear mesh frequency. But these lightning holes, because they're going to cause the stiffness to vary as you go around, give you really a carpet effect of stiffness is a function of which tooth, whether you're over a spoke or a slot, along with from the root to the tip. And so in a standard solid gear blank, we get these primary peaks of the gear mesh frequency. By having these slots, we see these added sidebands. And the FE approach allows us to capture those sidebands very accurately. Borrowing from Scott's world, because we have specialists in tests and specialists in simulation.
Just another example of where we work together well, Chris.
Exactly. We didn't just come up with this analytical approach by reading some papers. We actually built physical hardware, and we did testing and data measurements to correlate these numerical methods against the real world. So in this particular case, we've got a solid gear, and we've got the gear you saw pictured with the extreme slots, and we loaded them up with varying torque levels and measured some data. And what we found is with the pure analytical approach, the older methods, with this heavily slotted gear, it doesn't take into account the variation of tooth stiffness, and you can see versus the experimental data that we measured, the blue curve, we're not getting really that great. We're kind of getting okay correlation, maybe at lower torques, but as we increase the torque load and we look at the transmission error, we are not getting good correlation with the real world for transmission error. But with our FE method that lumps the tooth stiffness empirical approach with an FE method for the stiffness of the gear blank, you see our FE preprocessor method gives us very good correlation with the measured transmission error across the range of torques. And this is also with some parabolic crowning to reduce the line. So, Scott, another successful fundamentals of rotating machinery. Gears.
Yeah.
We've talked about some fundamentals. We've gone over some problems and where you could monitor those problems in your test data, and we've talked about some simulation methods.
Absolutely. Yeah, thanks for presenting with me again, Chris.
Always fun.